Hello and welcome to all students. In this lecture, we learn about separation of variables in the differential equation. If we have a differential equation, then by separating variables, we can solve the differential equation. So after all, we are looking towards a differential equation of first order and first degree. We begin our study of the method of solving first order equations by studying an equation of the form m dx plus n dy equal to 0, where m and n may be functions of both x and y, or sometimes they may be constants. Some equations of this type are so simple that they can be put in the form of ax dx plus by dy equal to 0, and this equation is in variable separable form because here variables are separated, that is the variables can be separated. Then a solution can be written at once for it is only a matter of finding a function f whose total derivative is the left member of equation 1. Then f is equal to c, where c is arbitrary constant, is a desired result. So if we are able to write our differential equation m dx plus n dy equal to 0 in the form of a x dx plus by dy equal to 0, means if we are able to separate the variables, then just take integration of equation 1, you will get the solution of that differential equation. So let us consider one example. Solve the differential equation dy by dx is equal to 2y upon x for x is greater than 0 and y is greater than 0. So this is first order first degree differential equation. We note that for the function in equation 2, the theorem of the previous section applies and assures that the existence of the unique continuous solution through any point in the first quadrant. By separating the variables, we can write dy by dy upon y is equal to 2 dx upon x. Hence we obtain a family of solution, and just take an integration, and we will get on the left hand side log y is equal to 2 times log x plus c. So this is the equation number 3. Or because we are in the first quadrant, we can write y equal to e to the power c into x square. If we note that, if we now put c1 is equal to e raised to c, we can write y equal to c1 x square, c1 is greater than 0. So this is the y equal to c1 x square, and this is the solution of the differential equation 2. Okay, so let us take another example. Example B. Solve the equation of the previous example. Solve the equation of the previous example for x not equal to 0. Okay, so this is the another example, and same example, but we are solving in the different case. So consider these examples number C. Solve the equation 1 plus y square dx plus 1 plus x square dy equal to 0, with the initial condition that when x is equal to 0 and y equal to minus 1. So these are initial conditions, and these initial conditions are useful to find the arbitrary constants in the differential equation. Okay, arbitrary constant in the differential equation. So if we write the equation in the form of dy upon dx is equal to minus 1 plus y square upon 1 plus x square, we observe that the right member and its partial derivative with respect to y are continuous near point 0 comma minus 1, and it follows that a unique solution exists for equation 8 that passes through the point 0 comma minus 1. From the differential equation we get dx upon 1 plus x square plus dy upon 1 plus y square equal to 0, from which it follows that at once that uh, just take a integration because variables are separated, and if we take integration we get tan inverse x plus tan inverse y is equal to 0. Okay, this is the solution of the differential equation, and by using initial conditions we can find the value of arbitrary constant c. Now let us go to the example D. Solve the initial value problem. 2x into bracket y plus 1 dx minus y into dy equal to 0 with initial condition x equal to 0 and y equal to minus 2. Just separate the variables and take integration. You will get the solution of the differential equation. So see here 2x dx is equal to 1 minus 1 upon y plus 1 dy, y not equal to minus 1. Integrating we get a family of solutions and gives the implicit and given implicitly by x square is equal to y minus log y plus 1 plus c. Using initial conditions we have the value of c is equal to 2. Put the value of c equal to 2 in our equation and in our solution, and we get the required solution x square is equal to y minus log y plus 1 plus 2. So these are the some exercise, and now we study about the homogeneous function. First of all we define what is meant by homogeneous function. So consider here a polynomials in which all terms are of the same degree. Homogeneous, this is the definition of homogeneous function. Polynomials in which all terms are of the same degree, such as see here first polynomial is x square plus 3xy plus 4y square. So in each term the degree of that term is 2. Now in next polynomial x cube plus y cube, in each term degree of each term is 3. Now consider the next example, x raised to 4 into y plus 7y raised to 5, and in this polynomial also in each term the degree of each term is 4, are called homogeneous polynomials. We wish now to extend the concept of homogeneity, so it will apply to functions other than polynomials. If we assign a physical dimension say length to each variable x and y in the polynomials in 1, then each of the polynomial itself also has a physical dimension length to some power. This suggests the desired generalization if when certain variables are thought of as lengths. A function has a physical dimension length to the kth power, then we shall call the function homogeneous of degree k in those variables. For example, the function f of x comma y equal to 2y cube into e raised to the power or exponent e raised to the power y by x minus x raised to 4 upon x plus 3y is of dimension length cube. When x and y are lengths, therefore the function is said to be homogeneous of degree 3 in x and y. We permit the degree k to be any number. The function square root x plus 4y is called homogeneous of degree 1/2 in x and y. The function the function x upon square root x square plus y square is a homogeneous of degree 0 in x and y. Okay, and a formal definition of homogeneity is a function f of x comma y is said to be homogeneous of degree k in x and y if and only if f of lambda x comma lambda y is equal to lambda raised to k into f of x comma y. The definition is easily extended to a function of more than two variables. For the function f of x comma y of equation 2, the formal definition of homogeneity leads us to consider f of lambda x into lambda y equal to 2 lambda cube y cube exponent lambda y divided by lambda x minus lambda raised to 4 x raised to 4 whole divided by lambda x plus 3 lambda y. But we see at once that f of lambda x comma lambda y equal to lambda cube into f of x comma y. Therefore, this function is a homogeneous function of degree 3 in x and y. As standard stated previously, the following theorem proves useful in the next section. Theorem says that if mxy and nxy are both homogeneous and of the same degree, the function mxy upon nxy is a homogeneous function of degree 0. Is a homogeneous function of degree 0. So that is important. Now let us go to the next. So here proof of that theorem is also given, so we can take a screenshot and we can study the proof. Okay, so some examples are given here, and just we have to check whether the given function is homogeneous or not, and if it is homogeneous then we have to state the degree of that function. Okay, now let us see the equations, differential equations with homogeneous coefficients. Okay, suppose that the coefficients m and n in the equation of order 1, means in the differential equation of first order and first degree, m dx plus n dy equal to 0 are both homogeneous functions and are of the same degree in x and y. By theorem 1 and 2 of the section 8, the ratio m upon n is a function of y upon x alone. Hence, equation 1 may be put in the form of dy by dx is equal to g upon y by x equal to 0. Thus, this suggests the introduction of a new variable v by putting y equal to vx then equation 2 becomes x into dv by dx plus v into g of v equal to 0, in which the variables are separable